In the last lecture, we were dealing with Maxwell's equations. We learnt that there is a discrepancy if there is only conduction current in the circuit. Maxwell said no, within the plates of the capacitor there should also be a current called displacement current, and the introduction of displacement current was very important because it showed us that the light is nothing but electromagnetic waves. In this lecture, we are going to start a new topic, optics, and the first part of optics is ray optics. But what is this ray optics? We shall see. In earlier classes, we are taught that light travels along straight lines. You see, you must have done those experiments. You have 2 or 3 cards and there are holes at the same height from the bench or from some surface, and you shine a light from this side and see from the other. You must have done those experiments showing that light travels along straight lines. Indeed, many simple experiments do show that light travels along straight lines. However, we know also that light is a wave. Light is, in fact, as you know, is an electromagnetic wave, it is a transverse wave. So, light is a wave. So, how do we reconcile the two things? It is found that as long as the aperture through which light has to pass has dimensions much larger than the wavelength of light, then the effects due to waves are not felt. Now, what is the wavelength of light? Say I take the middle of the spectrum of the white light spectrum, roughly 5.8 nanometers for yellow light. So, if the size of the aperture is much larger than 580 nanometers, much larger than that, then the waves will simply pass through without interacting with the aperture. However, near the ends of the aperture, the waves would still be bent, but if we ignore that, then through the aperture proper there is no change in the direction of the rays. Light goes as a straight line, and these straight lines are represented by rays, and whatever things we study using the approximation that light travels along straight lines or along straight rays is called ray optics, and we shall now start this ray optics. The first thing is very simple. Reflection of light is very familiar to you. When light falls on a surface separating two media, we have one medium here, another medium, let us say a glass plate or something, then light comes and changes its path, goes in another direction. We say the light has been reflected. The light falling on the surface is called the incident light falling on the surface, and that going in the other direction is called the reflected light. The angle between the incident ray and the normal to the reflecting surface is called the angle of incidence, and similarly the angle between the reflected ray and the normal at the point of incidence is called the angle of reflection. You see, this is the incident light, this comes, this is a boundary between two media. I have tried to show two different media by change in the shade. So, these are two different media, light comes and gets reflected in this direction. This is medium 1, this is medium 2, and this angle is the angle of incidence between the incident ray and the normal at the point of incidence, and this is the angle of reflection again between the normal and the reflected ray, and these two angles are equal. And the other law which governs reflection is that the incident ray, the reflected ray and the normal at the point of incidence, they lie in the same plane. What does it mean? It means this, that if we have this plane and there is another plane perpendicular to it, we have a plane, say a mirror, say here, and we have another plane, say mirror is placed here, one plane is this, the other plane is this, and let us say the light is incident, this is the point of incidence, there is a normal and gets reflected, that is the angle of reflection, and we say that incident ray, the normal at the point of incidence and the reflected ray, all three lie in the same plane. That is the content of the second law of reflection. and moreover if I is 0, then R is also equal to 0 because they are equal. So any light which is incident normally on the surface is reflected back along the same path. It needs to be remembered that only a part of light falling on any surface gets reflected. The rest is accounted for by absorption by the medium and transmission through the medium. A very highly polished surface like that of a glass mirror can reflect close to 100% light falling on it. Another thing to remember is that the laws of reflection are valid for any reflecting surface, whether that surface is plane or curved or any other form, doesn't matter. The law of reflection, that angle of incidence is equal to angle of reflection, is obeyed whatever the nature of the surface. The plane surface, here I have got the curved surface, light is incident like this on the outer say surface. This is the normal from the center of curvature, this is the normal, and the light gets reflected along this direction. Angle of incidence is once again equal to angle of reflection. So whatever the nature of the surface, the angle of incidence is always equal to the angle of reflection. Even if the surface is irregular like this, at each point of this irregular surface, the angle of incidence is equal to angle of reflection. I have done this, you can also do it. At each point find the normal to the surface and let the light be reflected, so that angle of incidence is equal to angle of reflection. So I have shown all the incident light is parallel, but the reflected light is not, it is diffused. So therefore this kind of reflection is called irregular or diffused reflection. But I have been asked several times this question: the angle of incidence is always equal to the angle of reflection. The laws of reflection are not violated. At each point this is true. However, when you take all the points along the surface, then you find that the reflected rays are diffused. That is why it is called diffused reflection. You remember that in one of the previous diagrams I had told you to ignore this, but now want to include this into the discussion. This ray which goes into the second medium is called the refracted ray. We say the light has been refracted from medium 1 to medium 2. And what are the relation between I and R? You know that relation, that if mu1 is the refractive index of medium 1 and mu2 is the refractive index of medium 2, then the relation is mu1 times sin I is equal to mu2 times sin R. Remember that R is in the second medium and I is in the first medium. So mu1 times sin I is equal to mu2 times sin R. This is Snell's law. The refractive index is taken as the measure of how optically dense a medium is. You see, perhaps you have noticed I have tried to show the optical density of the medium by these shades. This, for example, is optically denser than this one. Glass, which has a refractive index of 1.5, is optically denser medium than air, whose refractive index is 1.0003. The implication of Snell's law is that a light ray going from an optically rarer medium into an optically denser medium, it bends towards the normal. Why? Because the refractive index has to be greater than 1. Why? We will see in a moment. The ray going from a denser medium into a rarer medium bends away from the normal. So if it goes from rarer, then it bends towards the normal. If it goes from a denser medium, then it bends away from the normal. If you have 3 slabs, then say denser in between, then the ray first gets bent towards the normal and then away from the normal. Similarly, if the rarer is in between the 2 denser media, then the ray first, when it enters the rarer medium, it goes away from the normal and then it bends again towards the normal. And this is a very simple demonstration. You see, if you have a beaker of water or glass of water, and if you place a straw, let us say, then you see that straw is a little broken. Not only that, you also see that the end of the straw is slightly raised, as I have tried to show here. This is the ray going in. From T, this is a ray coming out, and if you are seeing from this, then this ray appears to be going in this direction. That means T is seen to be at I, that is, the end of this straw is slightly raised, and here it appears as if this straw is broken. Why does this happen? Let us look at this. To find the apparent depth of the object at O, so we have an object at O, we take two rays, we take ray OP and OQ. OQ is normal, therefore it gets reflected along the normal. This is at an angle of I to the normal, and therefore it gets bent through an angle R to the normal when it goes to the rarer medium, that is air. So we have I here, we have R here, and what do is I draw backwards the reflected ray. It meets this ray OQ at I. Therefore, I is the image of O. Image is formed wherever two rays either meet or appear to meet. Therefore, I is the image of O. It is a virtual image, obviously, because the two rays don't actually meet, but they appear to meet. If mu is the refractive index of the medium with respect to air, then we can write mu equal to sin R by sin I, and now you use geometry. Sin R is this, is QP by this, and sin I is QP by this. QP gets cancelled and you get OP by PI, and in the approximation of small angles you can write OP equal to OQ and PI equal to IQ, and IQ is OQ minus OI. So I do that, and then I can write the depth, the distance d by which the object seems to have been deviated is d, and therefore and T is the total thickness. So I can use this relation and write d equal to 1 minus 1 by mu times T. That is, if mu is, let us say, 3 by 2, then, and if T is 12, then d is 4 centimeter. That is, if a glass slab refractive index 1.5 is of thickness 12 centimeters, then an object placed at the end of the slab, at the bottom of the slab, appears to have been raised by 4 centimeters. That it appears from the top surface at the distance of 8 centimeters. Remember that there is always a certain amount of reflection whenever light meets a surface between two media. Maybe the reflection is small, but it is always reflected. Now let us answer this question: why does a ray bend towards the normal while going into the denser medium? The reason is that the speed of light in an optically denser medium is lower than in an optically rarer medium. So in this medium the velocity of light is smaller than in this medium. This is a lighter medium, this is a denser medium, and the speed of light here is smaller than the speed of light here, and therefore we can write down that equation and show that the bending is because the light travels here at a velocity which is smaller than the velocity here. So the physical meaning of refractive index of a medium is that it indicates the speed of light in that medium, and from Snell's law you can write sin I by sin R is mu 2 by mu 1, speed of light in medium 1 divided by the speed of light in medium 2. These angles are inversely proportional. You see, since the speed is here less, therefore the ray gets bent towards the normal. Mu in the air glass example is speed of light in air divided by speed of light in glass. If the refractive index of a certain type of glass is 1.5, then the speed of light is 3 10 to the power 8 divided by 1.5, that is C by mu, which is equal to 2 into 10 to the power 8 meters per second. Consider once again the interface between two media. The denser one in this case is above the rarer one. So incident light gets bent away from the normal as it enters the rarer medium, and if I keep on increasing the angle of incidence, at some angle of incidence the refracted ray will be along the interface. At that time this angle of incidence is called the critical angle, because now the angle of refraction is 90 degrees. If I increase the angle of incidence still further, then the light gets reflected in the same medium, it does not go to the other medium. Now, the angle of refraction is 90 degrees, therefore, we have sine of the critical angle is equal to mu 2 by mu 1 from Snell's law, and if mu 2 is air, then you have sine of IC is equal to 1 by mu. If I know the critical angle, if I can find the critical angle, then I can find the refractive index of this medium. So, just by finding out the critical angle at which the angle of refraction is 90 degrees, I can find the refractive index of that medium. Now, this is what is happening. If I keep increasing the angle of incidence, then there is what is known as total internal reflection. The reflection is internal to this medium, it does not go to the other medium. This is what happens in a medium which is in the form of a tube here. It goes like this, gets reflected again and comes out. So, this is what happens if there is total internal reflection. This phenomenon is called an total internal reflection, and the total internal reflection occurs only when light is incident on the interface from a denser to a rarer medium. Otherwise, this total internal reflection takes place only when light comes from a denser medium to a rarer medium and not otherwise. Here also you can see this is how rainbow is formed. You have a water drop, white light is coming, it enters the denser medium, and instead of going out, if the angle of incidence is larger than the angle of critical angle, then it gets totally internally reflected. It is a denser medium, outside air is a rarer medium. So, this kind of total internal reflection takes place only when light passes from a denser to a rarer medium. If you have travelled through a sandy desert, you might have experienced that you see the inverted image of trees and other objects from a distance. And when you go to that place, go to that point, there is no water. From a distance it appears as if there is water, because tree is reflected or other objects, say an electric pole for example, may be reflected as it is in water, but when you go to that point there is no water. That is why this phenomenon is called mirage. But what causes this phenomenon? In deserts, air near the ground is much hotter than at the higher level, and hotter air is rarer than the cooler air. So, there is a cooler air at the top, and then the temperature increases, therefore, there is cooler air is denser, then less dense, then less dense and less dense, and so on. So, there is a gradation, denser, less dense, less dense, less dense, and so on. And what is happening is that any ray coming from a tree or somewhere, it gets bent away progressively away from the normal till it reaches this layer, maybe the ground layer, and it gets reflected, because by this time the angle of incidence exceeds the critical angle of incidence, and therefore it gets reflected. This phenomenon of progressively increasing the angle of refraction, you can see that this angle of refraction becomes angle of incidence for this layer, and if this angle of incidence is larger than the critical angle for this medium and this medium, then the ray is get totally reflected. So, that is how the ray was coming like this and it is going like this, and if you are here you would see as if the ray is coming from this place, that is, there is a reflection as if in water, but there is no water. This total internal reflection has another interesting aspect. You see, if there is a treasure at the bottom of a pond, let us say, then you have to see only through this cone to see that treasure, otherwise you cannot see. And this Snell's law I can write as sin r equal to mu 1 by mu 2 times sin I, and if I plot sin r against sin I, then I get a straight line with the slope mu 1 mu 2. So, this is another method of finding the refractive index if I know sin r and sin I. In the next lecture we shall continue with the discussion of reflection and refraction, now from spherical surfaces.